Hi, ma'am. Hi, Sharayu. Hi, Professor.
Hi, can you hear me?
Yeah. Hello. Yeah, you're audible. One
Okay.
second. Let me grant you. So you are a co-host now.
Okay.
Can you please present your slides?
Yeah, let me try.
Yeah, your slides are visible.
Let me try going to full screen mode. Right now it's not in full screen, I presume, right?
Yes.
Okay. You see it in full screen mode now? Okay.
Yes,
Okay.
yes.
I'll just scroll a little bit. Let me know.
Yeah.
Changing?
Yes.
Okay. My audio is fine or?
Yes, Professor. Your audio is clear as
Okay.
well as video is also clear.
Okay.
I'm just delayed by a few minutes. Please give me some 5 minutes so that I will set up the arrangement.
Set up what?
Set up the arrangement. So,
Yeah, sure.
Professor, are you okay with broadcasting?
Yeah.
Sure. Let me do that. Thank
Okay. You want me to exit the call or stay
you.
on?
Please stay here.
Okay.
The rest.
Okay. I'm just muting myself then.
Yeah, sure.
These days. And given the compute and memory requirements of most deep learning models, these models are often installed and used on a cloud server, on an edge server, or some nearby server. However, if we could instead process and analyze this data locally, that would reduce the response time, reduce the network bandwidth usage, enhance privacy, and also improve scalability. This has initiated research efforts towards designing deep learning models that can be deployed on resource-limited end devices, for example, IoT sensors or smartphones, etc. We consider the following stylized system. We have an end device and one edge server. The end device has limited memory and limited compute power. This device periodically either senses, collects, or generates data and is tasked with performing multi-class classification on these data samples. The inference made on these samples is then used to make controlled decisions by the device itself. Now, compared to this end device, the edge server has significantly more storage as well as compute power. The device can communicate with the server via wireless communication channel, and since the channel is wireless, it is prone to communication delays. Recall that the end device periodically senses and collects data samples and is tasked with performing multi-class classification on these samples. To do this classification, which is an inference task, the system is equipped with two deep learning models. The device is embedded with what we call the local model, which is a lightweight model with limited accuracy. And the server is equipped with a state-of-the-art large, rich deep learning model. And this remote model has higher classification accuracy than the local model. For each data sample, the device has the option of either accepting the inference of the local model, we refer to this as the local inference, or instead it can enlist the help of the server and use the remote model for inference and work with what we call the remote inference. The big picture question we are trying to answer is where should we do the inference in such a system? Existing techniques for such inference tasks that can be done in a distributed manner can be classified into 4 basic strategies. There are more, but I'm limiting myself to these 4 for the purpose of this talk. The first is on-device inference. Here, you're doing all the inference locally on the end device without any support from any edge or cloud servers. There are a plethora of deep learning models that can be embedded on moderately powerful smartphones, and there are TinyML models that have been developed that can be embedded on extremely resource-limited IoT devices or even microcontroller units. However, due to their small size, these on-device or local models have poor inference accuracy and can often not be generalized or don't even have robustness to noise. The other extreme is the full offload model. Here, the idea is that all the inference is done on the server. This approach has high accuracy, but suffers from high latency. And this latency comes from the fact that all the samples have to be sent to the server, the inference has to be run on the server, and the final inference output has to be brought back to the device. So there is a two-way communication delay when we do full offload. The third option is load balancing, where a router decides where to send each sample. For example, one approach that has been looked at is to divide the computational load between the device and a server with the goal of minimizing the overall time or energy consumption per inference. Finally, the focus of this work is on the idea of hierarchical inference. Under hierarchical inference, for every sample, inference is first performed using the local model. Following this, depending on the output of the local model, if the decision module concludes that this inference is likely to be incorrect, then that sample is offloaded to the remote server for inference using the remote model. Now, this remote model is on an edge or a cloud server. Just to repeat myself, I want to emphasize the point that the main difference between load balancing and hierarchical inference is that under load balancing, each sample is sent to exactly one model. That is, each sample either goes to the local model or to the remote model. In contrast to this, under hierarchical inference, all samples go through the local model, and a subset of them are then offloaded to the remote model. Just for clarity, here is a detailed schematic of hierarchical inference. The purple box here denotes the end device. It has three important components. A local deep learning model for inference. This is a lightweight model. An HI decision module. HI here stands for hierarchical inference. The purpose of this module is that it decides whether to accept the local inference for a sample or to offload the sample to the server. The third important component of the end device is a control unit or a control module. This makes decisions based on the inference made by both the deep learning models. The orange box here is the server. The server hosts a more accurate and resource-intensive deep learning model, and we'll refer to this model as the remote model. Each incoming sample is first sent to the local model for inference. The local model outputs two things. It outputs a class for this sample as well as its own confidence in this classification. I'll elaborate a little bit on this the concept of confidence in the next slide. These two things are then fed to the HI decision module. The decision module then looks at the output and decides whether to accept the local inference or to offload the sample. If it decides to accept the local inference, the inference is sent to the control module, which then does whatever it needs to do with the inference. If the decision module decides to offload this sample, that is, if it decides that the local inference is not good enough and the sample needs to be sent to the server for inference, then the sample is sent to the remote model. The remote model runs its inference process and its result is sent back to the control module. Now, gauging the likelihood of the inference of the local model being incorrect is key to implementing hierarchical inference. In general, for every input, a deep learning model designed to carry out a multi-class classification task outputs scores for each of the possible classes. And these scores are often codified using what is called a score function. Now, the higher the score of a sample for a class, the more confident the model is in classifying that input to that class. Typically, in a multi-class classification model, each input is classified into the class for which the score is the highest. Now, post this classification, a confidence metric measures the confidence of the model in its inference for a given sample or a given input. The values of the score functions across classes are used to obtain this confidence. In general, the confidence is a deterministic function of the scores for that sample. For our simulations in this work, the confidence metric we've used is the maximum softmax value, which is a very widely used confidence metric, but our theoretical results hold for any confidence metric. To make these concepts more concrete, consider a multi-class classification problem where script C or calligraphic C is the set of possible classes into which we are trying to classify every model, every sample. Now, for each sample, the model generates a score for each class. So here, SC is the score for a particular sample for class C. And the model outputs the class with the highest score, which is the argmax of SC. And the confidence the model has in this classification is given by this expression here, which is called the maximum softmax value. By definition, the confidence value lies in the interval 0 to 1. As mentioned before, the focus of our work is on the HI decision module shown here. More specifically, we want to design policies that determine which samples to offload to the remote model for inference. One idea that has received some attention in the recent past is to offload the sample to the remote model if the confidence of the local model is low. And by low, we mean the confidence is below carefully chosen threshold. Now, if you want to work with these kind of decision modules, the obvious question is how low is low? Who decides what the threshold is? And of course, the answer depends on various factors, including the system parameters and the performance metric we're trying to optimize for. Before going into our work, I'll give you a quick overview of the kinds of things that have been looked at for this idea of hierarchical inference. There have been a handful of works that have been published over the past couple of years. In the first paper shown here, the authors present multiple use cases and show that hierarchical inference is indeed a promising approach. In the second work, the authors make the offloading decisions by computing a threshold offline using some training data set. And this threshold is used as a threshold for the maximum softmax value for each sample. In the third work, the authors show that the HI offloading decision can be improved by tweaking the confidence metric. So instead of looking at the max softmax value, they use a linear regression on the first two highest softmax values. Here also the threshold selection is done in an offline manner. The fourth work is a departure from the first three in the sense that here the threshold is computed in an online manner, which means no assumptions are made about the distribution of the incoming samples, and one has to decide what thresholds to use in an online manner in the hope that one can converge towards the optimal threshold. Here, the authors propose an algorithm by extending the celebrated hedge algorithm, and they provide a dataset dependent regret bound for their proposed policy. Finally, in the fifth work, the authors have extended the setting to multiple edge devices. Recall that our setting just has one end device. At a high level, one of the gaps our work plugs is that we propose policies with regret guarantees that are independent of the dataset. Further, the policies proposed in the fourth and the fifth work here are quite computationally expensive. And compared to this, the policies we propose are more efficient, thus making them more suitable for implementation on end devices. I'll now go into the details of our setting. Time is divided into rounds, and the following sequence of events occur in each round. The first thing is that the end device collects a sample. This sample is then fed to the local model for inference. The local model outputs its inference for that sample and its confidence in that inference. Using this as the input, the decision module then decides whether to offload this sample or to accept the local inference. If the decision is to offload, then the output of the remote model is received by the device by the end of the same round. So this entire process of first sampling, running local inference, deciding whether to offload or not, and then receiving the remote inference, all these four steps end before the next round begins. Recall that the confidence the local model has is a measure of its confidence in its own inference for that sample. One example that we saw before was the maximum softmax value. Note that multiple data samples may result in the same confidence value. In practice, this is often a result of the precision at which the scoring function values are stored. In this picture, we see that the possible confidence values are denoted by red crosses. Of course, these values lie between 0 and 1. Those confidence values that have been seen up to a certain time, say t, are in blue color. So these blue dots are confidence values that have been seen when the samples received thus far have been fed to the local model, and the local model spits out corresponding confidence values. The set of these blue dots is going to increase over time because more and more confidence values may be seen. For most of our theoretical results, we assume that these confidence values are generated by a stochastic IID process. Some of our theoretical results hold without these assumptions. And of course, for our simulation results, since we use real data sets, this assumption is not true, but our policies perform well even without this assumption. I'll go over our loss model now. Recall that in each round, the decision module decides either to accept the inference of the local model or to offload the sample to the remote model. And in each round, the system incurs a loss that is a function of this decision, as well as the inference of the local model and the remote model for that particular sample. Now I'm going to break down the loss model into three parts. There are three possible cases. Case one is this path in green in the right bottom corner. Here, the HI decision module has decided to accept the inference of the local model. And further, the inference of the local model and the inference of the remote model are actually the same. So in this case, the system incurs a loss of 0 units. This is the best case scenario, that the local model gave you an inference of the remote model, and therefore you kind of got the better answer. Red. This is the left bottom corner. Here, the decision module has decided to accept the inference of the local model as that of the remote model. So in this case, the system incurs a loss of 1 unit. The intuition behind this definition of the loss function in these two cases is the following. When we accept the inference of the local model, we work under the setting where actually the inference of the remote model is more likely to be correct. Further, we don't know the ground truth. So since the ground truth is not known, we use the output of the remote model as the benchmark. And if the local inference agrees with the remote inference, we assume sort of that it is correct. And if it disagrees with the remote inference, we assume that it is wrong. And therefore, the system incurs a loss of 1 unit. Now, the third case, the case in blue, is the case where the decision module decides to offload this sample. In this case, the system incurs a cost of lambda t. We refer to this as the offloading cost. And our setting allows this cost to be time varying. We restrict ourselves to a class of policies that we refer to as threshold policies. For any policy in this class, the decision in each round is governed by a single scalar value called the threshold. For each sample, if the confidence of the local model is above this threshold, the decision module accepts the inference. On the contrary, if the confidence of the local model for that sample is below this threshold, the sample is offloaded to the remote model. Note that the value of this threshold is allowed to evolve over time. There are some obvious trade-offs. If the value of the threshold is high, the system offloads a large number of samples, incurring high offloading cost. But in this case, the accuracy will be high. On the other side, if the value of the threshold is low, most inferences of the local model will be accepted, which leads to lower offloading cost. But since the local model is prone to errors, the system will probably end up incurring high cost, and this cost will be incurred every time the local model disagrees with the remote model. Particular input. I'm going to now define a subclass of threshold policies called fixed threshold policies. We say that a policy is a fixed threshold policy if the value over time. The algorithm challenge value of the threshold over time in an online manner. As a benchmark, we use the optimal fixed threshold policy. This is the policy that uses the same value of the threshold over time and minimizes the cumulative loss incurred in the time frame of interest. The performance metric we use is regret. Now, the way to parse this regret is the following. Consider any candidate policy, let's say P. We measure the loss incurred by the policy P in the first T rounds. The regret of the policy is then the difference between the expected loss incurred by the policy P and that incurred by the optimal fixed threshold policy. Note that both these losses have an expectation in front of them. This expectation is over the randomness in the exogenous processes. And for the policy P, this expectation is also over any randomness in the proposed online algorithm to determine the threshold. Needless to say, it follows that the lower the value of regret, the better the performance of the candidate policy. Before I get into the details of our contributions, here is an overview of our key results at a very high level. Recall that we restrict ourselves to a class of policies which we call threshold policies. For each sample, if the confidence is above the threshold, we accept the local inference. And if it's below this threshold, we offload the sample to the remote model. Note that the value of the threshold is allowed to evolve over time, and the algorithmic challenge is to learn the optimal value of the threshold over time in an online manner. We propose online algorithms with sublinear regret for this problem. In addition to our sort of theoretical results that only hold under certain assumptions, we show that our proposed policies perform well in conditions where these assumptions don't necessarily hold. To do this, we present simulations using standard data sets for the multi-class classification problem. Are there any questions at this point? Okay, I'll continue.
Professor,
yes,
a question here.
Yeah.
So how the remote inference is known before offloading to the remote edge server to define loss?
Yeah, so that's a very good point. When I get to the next module in this presentation, I'll address that point. It is, of course, an issue, and we figure a little patient with me. Are there any other questions?
Yeah, these are the only questions. Thank you.
Okay, then I'll move on. Okay, I'll address this question, but in a few minutes. Okay, so I'll move on. Now, before I go to describing our proposed policy, I'll go over a quick overview of the prediction with experts problem. And my motivation to do that is our policy actually builds on optimal policies for the experts problem. So I just wanted to give a quick primer to the relevant literature. For the moment, forget everything I said about hierarchical inference. For the next 2 slides, we're going to focus on a widely studied problem called prediction with experts. The setting is as follows. We have K experts, where K is finite. Time is divided into rounds. The algorithmic task is to pick one of the K experts in each round. After we do this, the environment adversarially generates a K-dimensional loss vector in each round, where the ith component of this vector is the loss incurred if we choose the ith expert in the round. Note that in each round, the loss vector is revealed only after we pick an expert for that round. Now we have some definitions here. We say that a policy is static if it chooses the same expert in all rounds. And the benchmark or the baseline for the problem is the optimal static policy. This is the policy which picks the same expert in every round and has the lowest cumulative loss in rounds 1 to T. The goal here again is to design an online policy which decides which expert to pick in every round, and we want to minimize the regret of this policy. The most widely studied policy for the prediction with experts problem is called hedge. It also goes by the name of the multiplicative weights algorithm. It works as follows. It maintains a weight for each of the K experts. This weight is denoted by W. In each round, the probability of an expert being the chosen expert is proportional to its weight. All weights are initialized to 1. And once the loss vector is revealed in a round, the weight of all the experts is updated as shown in the red line here. And this process is repeated in the next round. I'll give you a quick illustration for a small toy example where we have 3 experts. We start with the weights being 1 for all 3 experts, which means we're equally likely to pick any one of these 3. Let's say we end up picking expert 3. After we pick an expert, the losses are revealed. Here we are incurring the loss of 0.04 units since we picked expert 3. Based on these losses, we now update the weights using the expression in red in the box above. And in the second round, now we'll again choose one of the 3 experts with probability proportional to their weights. Let's say we end up picking expert 1. The loss vector is revealed. The loss of 0.2 units is incurred, and this process continues thereafter. Note that there is a parameter here, eta, that governs these weight updates. Eta is called the learning rate, and for the right value of eta, the hedge algorithm is known to be order optimal for the prediction with experts problem. Now let's go back to the hierarchical inference problem we started with. Recall that we had boiled down our hierarchical decision module to effectively picking the right threshold for the confidence values, where if the confidence value is below the threshold, we offload. If it's above the threshold, we accept. I now want you to think of these threshold values as experts, where if we choose a certain threshold or a certain expert in a given round, we incur the loss corresponding to using that threshold to decide whether to offload or not. Now, given this mapping between the experts problem and the hierarchical inference problem, an obvious question is, can we directly use hedge for our problem? And I'll answer this question in the coming slides. It will also answer the question that just came from the audience. I'm not sure who asked it. So I'll now go over the details of the algorithm we propose and also talk about our performance guarantees. Recall our loss model. Now, we do one of 2 things. We either offload or we accept. If we offload, that is, if we send a particular sample to the remote model, the inference of the remote model is conveyed back to the device. And therefore, the HI decision module can compute the loss value for all possible threshold values for that sample. The issue arises when we accept the inference of the local model. If we accept the inference of the local model, in this case, the inference of the remote model is not observed by the device. And therefore, in this case, we do not observe the loss value of all the experts. And therefore, we're not really in the expert setting. In the expert setting, the key characteristic is independent of the decision made by the learning agent, the losses of all experts are revealed in all rounds. Whereas here we see that when we decide to accept, that is when we choose a threshold that is lower than the confidence value for that particular sample, and we accept the local inference, we're not going to be able to decide whether the loss is 0 or 1. And the main issue with that is we never see the remote inference. And without the remote inference, it's not possible to conclude whether the local inference is the same as the remote inference or is not the same as the remote inference. I hope this answers the question. Now, here is how we address this issue. We make the following tweak to the hedge algorithm. We introduce forced exploration in each round. So what we do is, even if the confidence value is larger than the threshold chosen for that round, we still offload the sample with probability epsilon. So we generate X, which is a Bernoulli epsilon random variable. And if X is 1, we offload this model, even though we offload this sample, even though our confidence in the local inference for that sample is high. Okay. Note that even here with the forced exploration, the issue of partial information doesn't really get resolved. So even here, when we accept the local inference, we still don't learn the loss value for all the experts. And to address this, we maintain an estimate of the loss instead of the actual value of the loss. So let L denote the loss and let L hat be its estimate. We'll divide all the possible cases into three candidates. In case A, the estimate of the loss, L hat, is given the value of the loss itself. And we can do that in this case because when we offload, we know the losses for all the experts since we observe the remote inference. Case B is when we accept the local inference. In this case, we never observe the remote inference and therefore cannot compute the losses for all the experts. So in the absence of this information, we circumvent this by equating L hat to 0 for all experts. Finally, in the third case, which is when the confidence is high, it's higher than the threshold, but we offload it anyway because of forced exploration, we make L hat equal to L scaled by a factor of 1 over epsilon. What this scaling does is overall, it makes L hat an unbiased estimate of the loss function L. And in our variant of the hedge algorithm, which we propose for our problem, since we don't know the loss function, we use L hat instead as a proxy to update the weights for the experts. The second issue with implementing hedge on an end device is that the set of candidate threshold values, which is the set of experts, can be very large. And to address this limitation, we try to minimize the size of this set by exploiting the structure of the problem. Recall that our decision module offloads if the confidence we have for a particular inference for a sample is lower than the threshold for that round. In this picture, the red crosses denote the possible values the confidence metric can take. As before, the blue dots denote the confidence values seen up to the present round. So we'll see more and more of these blue dots popping up over time. Consider two threshold values. These are two potential threshold values, one in green called threshold 1 and one in yellow called threshold 2. Note that the decisions to accept or offload will be identical for these two threshold values because all potential confidence values are either going to lie to both their left side, in which case the confidence is too low and we'll end up offloading, or all confidence values will lie to the right. And for all the values to the right, if we use these two as the thresholds, we will end up accepting the local inference. Now, since both these thresholds are going to have the same sample path first, we don't need to consider these two thresholds as two different thresholds. And we can minimize the set of thresholds to a discrete set. And this set is in fact the set of values the confidence metric can take, which is the red crosses. So using the structural property, we've reduced the size of the threshold set to essentially these red crosses, which are the possible values the confidence metric can take. Secondly, look at these four threshold values marked in this picture. The leftmost is in blue. This is a confidence value that has been seen sometime before the current round. And the other three next to it are in red. These have not been seen up to the current round. They may show up sometime in the future. Now, due to the structure of our decision module, since it offloads if the confidence value is lower than the threshold, these four threshold values have the same cumulative loss up to the current round. So all these four threshold values are going to accept the local inference for all confidence values that lie to their right. And they're going to offload to the remote model for all confidence values that lie to the left. And since up to this time, there is no confidence value that lies between these four possible thresholds, 1 blue and 3 red, we can actually only consider the blue expert as a candidate. and say that the three other experts, the three experts in red, are the children of this blue threshold, which is called the parent threshold. And all the three children of the blue parent threshold have the same cost as the parent up to time t, if we're currently in round t. We exploit this structure to maintain a growing set of experts to implement hedge. What we do is, if the confidence value we see in a particular round is new, that is, it is a value that we haven't seen so far, we add a new expert with that confidence value. And this new expert inherits the cumulative loss of its parent up to that round. And its evolution beyond that point decouples from its parent. Now, putting all these pieces together, here is the algorithm we propose. We call this algorithm hedge HI. It has three salient features. One, we maintain a growing set of experts. If the confidence value in a round is new, we add it to the set of experts. Each new expert inherits the cumulative loss of its parent up to that time. The second feature is that we've added forced exploration in each round. And to address the issue of partial observation, we maintain an estimate of the loss. This estimate we denote by L hat, and we've shown that our estimate is an unbiased estimate of the loss function. And finally, the third piece of the puzzle is that since we don't know the loss function, we use its estimate, the L hats, to implement the hedge algorithm. Here are our performance guarantees for hedge HI. The input parameters for the algorithm are the learning rate, eta, and the forced exploration probability, epsilon. Another important quantity for our analytical result is the number of unique confidence values observed up to time t. We denote this by n subscript capital T. Our first theorem states that there exists values of eta and epsilon for which the regret of hedge HI scales as t to the 2/3 times the expected value of nt to the power 1/3. Note that in our setting, the set of values the thresholds can take, or the set of values the confidence metric can take, are finite. And therefore, even if we don't know the expected value of n subscript t, it is upper bounded by a constant, and it follows that the regret of hedge HI is sublinear. One limitation of this result is that the expected value of nt may not be known. And unless we know that, it's not clear as to what learning rate we should use when we implement this algorithm in practice. We essentially need a proxy for it to compute eta. And I'll elaborate on this point when we present our simulation results. One property of this algorithm we proposed, hedge HI, is that the set of experts can potentially grow to the set of all possible values the confidence metric can take. And this itself may be prohibitively large in some settings, especially when the end devices are really small and have very little memory and compute power. To address this, we propose a variant of hedge HI, and we call it hedge HI restart, where the key idea is to freeze this set of experts after some time tau. Tau has to be carefully which is the time at which the set of experts is frozen, the learning rate eta, and the forced exploration probability epsilon. What hedge HI restart does is that it just mimics hedge HI up to round tau. There's nothing new that happens. After round tau, the algorithm freezes the set of experts to those confidence values that have been observed up to time tau. It resets all the weights to 1. And in subsequent rounds, it mimics hedge HI, but it does not keep adding new experts to the set of experts. It essentially uses a set of experts that have come up to time tau. Now, choosing the right value of tau is key here. For large tau, the set of experts may be too large, while for small values of tau, we may miss the optimal expert, which will lead to poor regret performance. Here are our performance guarantees for hedge HI restart. Now, since the algorithm is a bit more limited, this theorem holds only under an additional assumption. And that assumption is that the probability of the confidence value in a round being equal to the optimal threshold value is lower bounded by a quantity nu that is strictly larger than 0, strictly positive. Under this assumption, we show that there exists value of eta, tau, and epsilon for which hedge HI restart has sublinear regret. We have characterized the explicit values of tau, eta, and epsilon. I've suppressed them here just for clarity. In the interest of time, I'm skipping the details of the proof, but here is a summary of our analytical results. We propose two algorithms. One is called hedge HI, the other is called hedge HI restart. The key difference between them is how the set of experts evolve. This set stops growing after round tau for hedge HI restart, but for hedge HI, it continues to grow and can potentially grow to the set of all possible confidence values that can be generated by the local model. Both regret bounds are sublinear, but we see that the regret bound we have for hedge HI restart increases at a slower rate with the size of the set of experts. It comes at a cost though. This guarantee for hedge HI restart only holds under an additional assumption on the probability of the confidence value in a round being equal to the optimal threshold value. I'm reminding you that one more issue, I've already mentioned this, is that some of these results require the knowledge of the expected value of NT, which is the expected value of the experts at time t, which is not necessarily known. We deal with this limitation by using a proxy for the expected value of NT in our numerical results, and I'll present those results now. We use the ImageNet dataset. Again, we're carrying out multi-class classification. Our local model is an 8-bit quantized model. The accuracy of this model is 35%. The model outputs 8-bit scores, and the number of possible distinct confidence values is also 2 to the power 8, 256. The model is 500 KB in size. The loss for offloading, which is the offloading cost, here we've taken it to be a constant. And if you recall, one of the issues we need to address is what learning rate to use when we don't have a handle on what the expected value of NT is. So for these set of simulation results, we just use the upper bound of 256 as the expected value of NT. It's just a proxy since we don't know the expected value of NT for any given setting. The time horizon of interest here is 10,000 rounds. Recall that we have two policies. Pi h here denotes the hedge HI algorithm. Pi hr is the hedge HI restart algorithm. We use two different values of tau, 100 and 500. We compare the performance of these two policies with 4 other policies. On device accepts all local inferences. Full offload, this policy offloads all samples to the server. Theta star is the optimal fixed threshold algorithm. So we find the optimal value of the threshold offline and then use that as the threshold throughout. So theta star has more information than the other policies. And the fourth, which I have denoted here in blue by HI, is an algorithm that has been proposed in one of the prior works I discussed initially. So we compare the performance of the 4 algorithms in terms of the normalized cumulative loss. We see that these hierarchical inference-based approaches outperform full offload and on-device for all values of the offloading cost considered. We also see that the cumulative loss of the two of our algorithms, hedge-HI and hedge-HI restart, is comparable to that of theta star. Theta star is an offline policy, so it has more information than our online policies, and yet we don't see too much of a performance degradation. Further, if you look at HI, which is an algorithm from prior work, our algorithms have performance very close to that of HI in terms of the cumulative loss. Our algorithms do have an advantage over HI, which I'll highlight in the next slide. Here is the runtime comparison of these algorithms. So this is the average amount of time needed to run the algorithm which decides what threshold to use. So here we see that since for hedge-HI restart, the expected set can only grow up to time tau, the time for inference for hedge-HI restart stabilizes after time tau because the set of experts is not growing anymore. But for hedge-HI and HI, which is from prior work, we see that this the time per inference keeps increasing. It also saturates at some point, and this is the point at which all the distinct confidence values have been revealed. So effectively, the set of experts is frozen for these policies also beyond that time. Finally, in the last result I'll present, we study the effect of the restart time tau for the hedge-HI restart algorithm on its performance. We plot cumulative loss as a function of tau. As expected, the larger the value of tau, lower the loss. But we see that we get fairly good performance for quite low values of tau, and the rate of improvement slows down as tau increases. So the takeaway here can be that for this particular data set, you can use very reasonable values of tau, which will keep your expert set limited, yet get fairly decent performance. I'll end with a quick recap of our problem and our contributions. Our system had two main components, an end device with a lightweight local model, an edge server with a rich remote model. And the question we were trying to answer is, where do we do the inference on the samples that are collected by this end device? We focused on the decision module in an hierarchical inference setting. Under hierarchical inference, all samples are first sent to the local model. Depending on the output of the local model, a subset of these samples are then offloaded to the remote model. We restrict ourselves to a class of policies that we call threshold policies. For each sample, if the confidence of the local model is below a threshold, we offload it, else we accept the local inference. And the value of this threshold is allowed to evolve over time. Now, choosing the right value of the threshold over time is the key challenge in our system. And we propose variants of the celebrated hedge algorithm and show that those variants have sublinear regret. Further, simulations also show that our policies perform well in practice. There are some implications of our work for the prediction with experts problem, the original problem I discussed, but I'll skip those in the interest of time. If there are questions, I'll be happy to take them. Thank you.
Thanks a lot, Professor, for a very detailed and an informative talk. I request the audience to feel free to ask questions if there are any. So, I guess there are no more questions, Professor.
I have a question.
Yes,
Anurag Kumar here. Can I come in?
Yes, sir. Please.
I can hear you.
Yeah. So in the beginning, first of all, very interesting collection of problems that you worked on, Sharayu. But I have one. I think I missed something somewhere.
Okay.
In the very beginning, you motivated the split between the local processing and remote processing by having a wireless network in between.
Yes.
Presumably, because of the wireless network, something is lost if you send the data across.
Yes.
But since you don't model a wireless network, it is not really clear. I guess if you split the inference between the sensor and the remote, overall, it can't be better than sending everything to the remote, because there's nothing modeled which loses by sending everything to the remote, right? So something
Okay.
there, yeah.
Okay. I just pulled up my slide on the loss model. Is it visible?
Yeah.
Yeah. Okay. So here, there are three possible cases. Case 1 and 2 are when you accept. And the way we've modeled the cost the system incurs for offloading, which is sending to the remote model, is that every time we offload, we incur a cost lambda t.
Okay.
Which can vary over time. So this could be the cost of transmission or delay or whatever you want to call it. This is how we capture the fact that offloading leads to both you may have to use power to transmit, and there will be latency. Both of that is captured through this lambda t loss.
Okay. Okay. Thank you. I understand now.
Okay. Thanks.
Any more questions? Okay. I guess there are no more questions, Professor.
Okay.
Thanks a lot once again for accepting our invitation. And the audience, thanks a lot for your time, and have a great evening. Thank you.
Thanks. Bye.
Bye.